Happy Wednesday. Today we're going to go over molecular composition of gases, and I will not be providing this note sheet on PowerSchool Learning, so you're just going to have to write it on a separate sheet or in your notebook. To start, we have our equation here. It's already balanced. And to talk about the molecular composition and just getting into molar volume, Avogadro's law, we know from stoichiometry that this is like saying 2 moles. For every 2 moles of hydrogen, 1 mole of oxygen would produce 2 moles of water vapor. Now, with things like our Gay-Lussac law of combining volumes of gases, really long name there, not just our Gay-Lussac law. If we have a gas at constant temperature and pressure, the volumes of these gases can be expressed as small whole number ratios, meaning we can make these volumes instead. We could say we have 2 liters for every 1 liter of oxygen, which then would produce 2 liters of H2O. We could change these into milliliters, so it only has to deal with the volumes. If I have 4 milliliters, I still need that 2-to-1 ratio, meaning I would need 2 milliliters to produce 4 milliliters of water. And that is this first law that helps kind of get a shortcut to some of the stoichiometry we're going to do a little bit later. Avogadro's law, our next one, is where equal volumes of gases at the same temperature and pressure contain equal number of molecules. We know that 1 mole equals 6.02 times 10 to the 23rd. If we have 2 gases with 6.02 times 10 to the 23rd, we have moles. So if we have the same number of molecules, formula units, atoms, we would have the same number of moles. That's because the volumes of gases and moles are going to be directly related. So V over N would equal some constant, our volume, over N. This looks very similar to Charles' law, where we have volume over temperature, but now we have N. We have a different variable here, and N is moles. Avogadro's law then gets us into molar volume, and at the beginning of this, or when we were going over mole conversions, I showed you my little flow chart here. You know particles, atoms, molecules, formula units, and mass. The third spot is for volume. Molar volume is only for gases at STP, so standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, which 0 degrees Celsius is 273 Kelvin. 1 mole of any gas at STP is going to occupy 22.4 liters. Our conversion factor here, 1 mole equals 22.4 liters. Liters could also be written decimeters cubed for the volume. And then let's say we have milliliters. 1 mole is going to be equal to 22,400 milliliters, and a milliliter is the same as a centimeter cubed. This will be our conversion factor. Example 1, calculate the volume of 7.1 moles of nitrogen gas at STP. I'm given moles. I'm trying to find volume. And if it doesn't specify whether liters, milliliters, centimeters cubed, you can pick any of these. Again, just my given, and to find, I'm starting at moles. I need to go to volume. Write out my steps, and we'll go to liters. and set up my dimensional analysis there. What we're given always goes in that first box. We have 7.1 moles. Same color, same unit. Mole. And then we're trying to find that volume, which is liters. Here's where I'm going to use that conversion factor. Keep in mind that the unit tells you which number you're going to put there. If we're using this conversion factor, 1 goes with mole, and then 22.4 will go with liters. Then I cancel and multiply everything on top, divide by the bottom, and we should get, when I calculate this out, $159.04 liters. So that's the first example for molar volume. The next one we have is an experiment produced 98 milliliters of SO2 gas at STP. We want to calculate the mass of SO2 produced. I'm trying to find the mass. This is an extra step. Where I'm starting is in yellow. I'm starting at milliliters, which is a volume, so this could also be milliliters. And then in my arrows, I have my 22.4 liters, just so I know that. But volume, I need to get to mass. There is no arrow that goes this way. I have to go from volume to moles to mass. I'm going to go milliliters, moles to grams. Where I have my arrows, my vertical lines, and across. What I'm given, always in that first box, 98 milliliters. I need to cancel those units. So everything in yellow is going to have a unit that cancels. Milliliter. Then moles. And I said this during stoichiometry and in conversions, or just mole conversions. My steps that I write here are also the units that go in these top boxes. So we have moles, and then we're trying to find that mass, which is grams. For this, we need a conversion factor. I know that 1 mole is equal to this many milliliters. So 1 will go with mole, and then we'll do our 22,400 milliliters. And then mole here. We have grams and moles. I need to look for the molar mass on my periodic table. 1 mole. In 1 mole of SO2, to find out how many grams there are, we're going to take the mass of sulfur and add it to the mass of 2 oxygen, which sulfur is about 32, oxygen is 16 if I have 2 of them. 32 plus 32 is 64. Moles and milliliters cancel, so we're left with grams. Multiply everything on top, divide it by the bottom, which would just end up being 22,400, 98. And we should get 0.28 grams SO2. So this is kind of a review on our dimensional analysis that we used to convert with and do stoichiometry, because that's what we will do tomorrow.